Scientific Visual is glad to provide another educational video on smart crystal processing. I will explain the smart wafering approach that enables us to harvest more defect-free wafers from industrial crystals. When there are few defects in the processed core, their positioning to the cutting planes matter. Let us benefit from this effect. Knowing the precise defect coordinates allows calculating a core offset to position more defects into sawing gaps and out of future wafers. Let me illustrate the mechanism of such a gain with a simple animation. Assume we are to wafer a crystal core with a regular grid of blades or cutting wires. We set up the grid to obtain wafers of thickness T, and the wafering process will make a gap G between the wafers. The G stands for the material that will be removed at wafering. Assume our core has a few volume defects, for example, a bubble or a microcrack, which makes the corresponding wafer defective. It would be useful to put as many defects in the gap as possible so they get removed, right? So, we could slightly shift the core along the grid and see that when some defects end in the gap, we get an extra defect-free wafer. The number of defect-free wafers varies when we shift the core in the grid. Therefore, we could compute an optimal shift for each defective core that provides a maximum of defect-free wafers. How many extra wafers could we actually get, you ask? Let's check on a real crystal. This is a digital twin of a 4-inch sapphire core of 180 millimeters length. It is cored out of a large KY sapphire crystal. It needs to be wafered to 1.8 millimeter thick wafers, and the wire machine provides a 0.7 millimeter gap. It is opened in the yield software that could simulate coring and wafering. Let's start with a traditional blind wafering with no shift. We got a total of 72 wafers. Among them, 6 are defective and 66 are quality. Now let's slightly offset the core and do wafering again. The only parameter to control is the offset of the first cutting plane to the edge of the core. We got the same total, 72 wafers. Among them, 4 are defective and 68 are quality. We harvested 2 more wafers, therefore increasing the wafering yield by 3%. Now, let's opt for the smart wafering routine in the yield software. It will scan all possible wafering options and find the best one. This is the plot showing offsets versus gains. On the horizontal axis, you see the possible offset values, and on the vertical one, the number of non-defective wafers. The red point indicates the optimal shift. It is 0.7 millimeters in our case, which gets us plus 3 wafers, therefore a 4.5% increase in the yield. All that's left is to fix the core in a wafering machine and benefit. This method allows up to a double-digit increase in the wafer output without growing or buying new crystals. The vital prerequisite is having a high-precision digital twin of your crystal. Scientific Visual is a Swiss metrology company supplying automated scanners for industrial crystals. The scanners make digital twins of raw crystal cores and ingots, allowing this and other optimization methods. This time we demonstrated the technology on a sapphire core, but it's also applicable to multiple semiconductor and optical crystals. Send us your crystal for a test inspection now and discover how digital quality control will help to increase your production yield.